We are live. All right. So hello, everyone, and welcome once again to the Latin American Webinars on Physics. I'm Joel Jones from the PUCP in Peru, and I'll be your host today. So today we're having our last webinar of the season. It is webinar 99. So I'm very happy to be the host today, but not only for this reason, but also because we're having Paola Ferrario as a speaker, right? So, well, Paola moved to Valencia, Spain in 2006 in order to do her PhD. And since then, she joined an experiment searching for neutrinoless double beta decay called the NEXT, right? And it's currently operating at the Canfranc Underground Laboratory. In 2017, Paola obtained an ERC starting grant to develop a PET scan prototype based on liquid xenon, which is the main protagonist of NEXT. So this project has been named PETALO and applies particle physics technologies to medical imaging. She's currently affiliated to the Donostia International Physics Center and Ikerbasque. So, of course, today Paola will tell us about NEXT and the link with PETALO. So before we begin, let me remind everybody that you can ask questions and comments via the YouTube live chat system. And we will pass the questions to Paola at the end of her talk. So we're all yours, Paola.
Okay, thank you, Joel. Let me share my screen. Well, I'm happy to be here today. Thanks for the kind invitation. So, okay, can you see my screen?
Yes.
Right.
Perfect.
Okay, so thanks for being here today. I hope you are doing well in this strange situation we are all in. So I know that for somebody it's difficult also to find some time to attend the seminar. So thank you, everybody. So today I would like to talk about these two projects I'm involved in, which apparently they could appear very different between them, but I hope in this seminar to convey that they are not so. So let me start with the first project that is about neutrinos. So just to remind you, neutrinos are a very interesting particle. They were proposed, their existence was proposed by Pauli in the 30s of the last century, because there was a problem in nuclear physics. They were observing a beta decay, which is a very common nuclear decay, where an electron is emitted. And they were looking at the energy of the electron, and instead of finding always the same energy, which would be what one expects for the conservation of energy, they would find a continuum of energies. So this was a problem because either energy was not conserved or there was some missing energy somewhere. So Pauli wrote this now famous letter to a conference in Tübingen that starts with dear radioactive ladies and gentlemen, and he proposed that a new particle exists which would be the responsible of carrying away this missing energy. Of course, this particle was not seen, so this particle should be not detectable and have no electric charge also. So he, in himself, he said, I've done something very bad today by proposing a particle that cannot be detected. It's something that no theorist should ever do. Well, actually, fortunately, Pauli was wrong. And in fact, neutrinos, as they were baptized by Fermi a few years later from the Italian little neutral one, neutrinos were actually detected experimentally. The first time was in 1956 with the experiment of Cohen and Rines that detected reactor neutrinos first. And since then, we have learned a lot about them. We know that neutrinos don't have electric charge. They only suffer weak interactions. They are produced in nature, in radioactive decays, in nuclear reactions, such as those that happen in stars. We know that neutrinos have a mass, although a very tiny one, and we don't know still the absolute value of this mass. So a few years after the introduction of neutrino by Pauli in 1935, Maria Gopper-Mayer proposes the existence of a decay that is very closely related to the beta decay we were talking about before, the double beta decay. I mean, she proposes that in one single nucleus, two beta decay happen at the same time. This is something, this process, this double beta decay, is something that is very slow and is strongly suppressed in most of the nuclei of the isotopes in nature. Because single beta decay is much more intense, and so it overcomes the other signal. However, there are some nuclei with even mass number, and specifically nuclei where either protons and neutrons are even, where the nuclear pairing energy forbids beta decay. So double beta decay is favored energetically, and then we have the possibility of measuring this decay. In fact, this decay is a decay where two electrons are emitted in the same nucleus, together with two antineutrinos. This decay has been measured in a number of isotopes since the 80s, and it has a long half-life, around between 10 to the 18 and 10 to the 21 years, but it is measurable, and it has been done so in several isotopes. So 2 years later, here there is the third character of the history of neutrinos, is Ettore Majorana. He's a young Italian, a brilliant mind, according to Fermi. He disappeared mysteriously in the late 30s, and we never heard about him. But before that, he proposed that neutral fermions with spin 1/2 could be their own antiparticle, meaning that neutrinos being neutral could be their own antiparticle and be the same as the antineutrino. And for this reason, in honor to Ettore, we call this property to be a Majorana particle. So if neutrinos are the same as antineutrinos, actually the double beta decay could happen without the emission of neutrinos, as you can see here. And this process, so far hypothetical, would be a process that violates lepton number and requires massive neutrinos. So why is this kind of process, the neutrinoless double beta decay, interesting? Well, because if neutrinos are Majorana particle, they would play a role, an important role in understanding one of the problems of physics nowadays, that is to understand why universe is made of matter instead of antimatter, or instead of having the same amount of matter and antimatter. What we know from observation is that we are made of matter, electrons, protons, and we are able to create antimatter. Antimatter is created in nature as well. And it's created always in the same amount, matter and antimatter. Also, due to inflation at the beginning of the history of the universe, it is thought that any possible anisotropy before would have been smashed out. And so at the beginning of the history of the universe, we think that we had the same amount of matter and antimatter, a situation of equilibrium. So the question is, what happened that that created an excess of matter that have evolved and has originated the universe as we know it? So there are several conditions for this process to happen, and here Majorana neutrinos come into play, because if neutrinos are the same as antineutrinos, they could decay to both leptons and antileptons. If there is a mechanism that favors the creation of leptons over antileptons, some mechanism of CP violation, then this excess of leptons could convert into an excess of baryons, and create this excess of matter over antimatter. So the most practical way of determining if a neutrino is a Majorana particle is to look for the neutrinoless double beta decay, which is what next is the objective of next. So in any neutrinoless double beta decay experiment, what one wants to measure is the two electrons of the decay that are emitted. So we want to measure their energy, because we know that their energy is always the same because no neutrinos are in the process. Instead, in the conventional double beta decay, we have a continuum of energy as shown in this picture, in this plot. We see the continuum of energy of the electrons in the two neutrino double beta decay, and then we see the peak in the end point of this decay. So you can see that if this decay, if this spectrum overlaps the peak, it's very difficult to distinguish the no-neutrino double beta decay from the two neutrino one. So one characteristic of any experiment of neutrinoless double beta decay is to have a very good and excellent energy resolution in order to go and find and look for the decay just in this little region. The second problem of these experiments is that this decay, if it exists, is very, very rare. So we have a lot of natural radioactivity all over the place that is a background for this experiment, because natural radioactivity, especially uranium and thorium chains, emit gammas with energies up to 3 MeV, which is usually above the endpoint energy of the spectrum. And these gammas convert into electrons, and so they mimic the signal of the two electrons that we want to see. So another characteristic of a double beta decay experiment is that it has to reduce the background as much as possible. It is really like finding a needle in a haystack. For this reason, what one does is to go underground in underground laboratories. So the rock of the laboratory is what screens you from the external radiation, but it is not enough because the rock itself emits radiation. So you need to shield your detector with some protection inside the lab, but this is not enough because the shielding itself emits radiation. So it's like a Russian doll game where you build layers of protections more and more pure, radioactively pure, so that the inside of your detector is as protected as possible. So here is let me introduce to the collaboration, the next collaboration. We are an international collaboration with a big contribution from Spain and the US. And we have our detector at the Canfranc Underground Laboratory. It is in the Spanish Pyrenees, and we use the old train railway that you can see here in the picture to access the lab, which is inside the mountain. This is a picture of the external lab. So in NEXT, we use a specific isotope of xenon, xenon 136, which has the double beta decay and can have the neutrinoless double beta decay. What are the characteristics of this isotope compared to others? Other experiments use other isotopes and other techniques. So in xenon is very interesting because it has a high Q value, meaning the endpoint spectrum, the energy of the endpoint spectrum is quite high, so it's very close to 3 MeV. So most of the low energy background, we can get rid of it, just looking at the energy. The two neutrino mode is low, so it doesn't bother too much. And it's also easy to enrich because in nature, naturally the abundance of this particular isotope is 9%. So we need to enrich it, but there is already some amount in nature, and it's not so difficult to and expensive to enrich. So as far as the two characteristics I mentioned before, for energy resolution, gaseous xenon is very good because the fluctuations in the production of the ionization signal are very low, sub-Poissonian. So as you can see in these pictures, we are, let's say, in the right situation where the spectrum of the two neutrino mode falls almost outside the peak of the energy that we are looking for. So we have a good energy resolution. And the second important thing is that in gaseous xenon, we can actually make a picture of the electrons, meaning that electrons go through the xenon with a path that is several centimeters long in 15 bar, which is the operation pressure of next. It is around 10, 15 centimeter long. So we can see the deposition of energy of the electrons. And this is important to discriminate signal from background. Let me remind you, the signal is two electrons coming from the same point, while the background is a single electron that comes from a gamma that interacts with photoelectric effects or Compton effect, Compton process in the gas. So electrons, they deposit the energy almost at the same rate along their path until the very end, where they release all of a sudden the remaining energy. So you can see, for instance, that the signal appear with like a spaghetti. I mean, this path that is more or less the same energy. And then at the end, you can see a higher amount of energy that is represented by the lighter color here. Instead, background, since it's single electron, will have only one end with the higher energy, and the other end is just normal rate energy deposition. Okay, so this is something that is very specific of gaseous xenon. You cannot do this in liquid detectors, for instance, because all of the electrons are just points, so you cannot distinguish the energy deposition. Okay, so how are we going to detect this electron? We use a high pressure xenon time projection chamber using electroluminescence to amplify the signal. So a time projection chamber is just a cylinder of steel filled with high pressure gas, xenon gas. And we have at the two ends of the cylinder, we put sensors, photosensors. On one hand, we have photomultipliers, which are big sensors that measure the energy of the events. And on the other hand, we have silicon photomultipliers, which are smaller sensors, and they give us the tracking of the events, meaning they allow us to reconstruct the position of the event in the chamber. When a charged particle is propagated in the gas, it releases its energy with two mechanisms. It produces scintillation in the gas. In the case of xenon, are photons in the UV range, ultraviolet range, and also ionizes the atoms of the gas. So also electrons are extracted from the atoms of xenon. So as for scintillation, you can see here in the cartoon, the photons jumps all over the chamber. We have reflective walls so that these photons are not lost, but they are reflected, and they end up on the photomultipliers on one hand. And this scintillation light gives us the starting time of the event. So when photomultipliers detect this light, we say, okay, the event starts here. On the other hand, the ionization electrons are drifted by an electric field, which is applied from the cathode to here, to the beginning of the ear region. They are drifted. And when they arrive to this yellow region, the electroluminescence region, they undergo a more intense electric field. So they are accelerated, and a second scintillation occurs. This is what we call electroluminescence. Now, this scintillation is much more intense than the first one, so we can actually do a measurement of the energy through this scintillation light. The photomultipliers detect this light with a very high precision. They have very low fluctuation, so we can have a very good energy resolution. And we can say this event has this energy and see if it falls inside our peak or not. On the other hand, the silicon photomultipliers, which are very small, 1 millimeter squared area, and they are like an array so at fixed pitch, one from the other. At each instant, this silicon PMs gives you a pattern of light. So from this pattern of light, you can reconstruct the position of the point that generated this light. And you do it every time. In this way, if you put all this information together, you can reconstruct a 3D image of your track, of your electron. And so use it for the discrimination from background. So this is how a signaling next appear. This is time, this arrow. So first, the primary scintillation happens. You see that is very small compared to the other one. It is just to say this is the starting time of the event. Then the drift occurs, and after this period of time, the secondary scintillation happens. This is much more complicated because you can see the projection. This is why it's called time projection chamber. The projection of the track, time by time. Each moment of time corresponds to a position in the chamber. And this is the energy that is recorded, the charge that is recorded at each position. And this is the electroluminescence signal. So this is a picture of our first detector that we put in Canfranc. This is actually underground. It's called Next White, also known as NEW. It's the world's largest pressure TPC. And the aim of this first prototype was to test the background model that we created with our Monte Carlo simulation. So we have now measured actually which background we have in the laboratory after all this shielding I've talked before. Second, we want to measure the 2 neutrino double beta decay, and to test the technology for the next step, which is the big detector of 100 kilograms of xenon. In this detector, there are around 5 kilograms of xenon circulating. So here are a few pictures of NEW. You can see here part of this shielding I was talking about. This is copper, ultra radio pure copper that we need to shield the gas from the radiation that comes from the vessel itself. This is the light tube, a tube of Teflon that reflects the light, so improves our light collection. This is also the light tube with the PMTs, the photomultipliers on the back. The light that you see here is blue because we need to shift the ultraviolet light of xenon to a wavelength that is more close to blue to have a better light collection, a better propagation through the materials, and a better photodetection efficiency. To do so, we cover all this tube with a molecule, an organic molecule TPB, which is a wavelength shifter that actually does exactly that, converts a photon that is in the UV range to a photon that is blue. This is why you see this nice blue color. These are the photosensors of NEXT, which are what allows us to get the signal. These are the photomultipliers, what we call the energy plane that measure the energy. You see that they are big because what you want here is to maximize the coverage and collect as much light as possible. And here you see the silicon photomultipliers, while you see the boards on which they are mounted. And you see that they are very tiny and a fixed space in order to give you the tracking. So let me show you the results that we have obtained so far in Canfranc. First of all, we have measured the energy resolution with calibration sources, and we get an excellent energy resolution, better than 1% full width al maximum at an energy that is very close to the energy of the neutrinoless double beta decay. The energy of neutrinoless double beta decay is around here, and we have a calibration source that gives us gammas at this energy. So we are pretty confident that we will get the same energy resolution. This is the best resolution that have been reached in experiments with the xenon 136. Second, here you can see what I was talking about before, the tracks of the electrons. This is actual data, and these are electrons of the 2 neutrino double beta decay. You see the 2 energy depositions at the end of the track. On the bottom part, you can see single electrons. So you see one energy deposition at the end of the track. And this way, we are able to add a further discrimination and find a better, cleaner sample of signal. How did we demonstrate that this discrimination is possible? Well, we used also calibration sources. In fact, the thallium-208 calibration source is very interesting because it emits a high energy gamma. This gamma has some probability of doing pair production in the gas. So you have an electron and a positron. And positrons behave very similar to electrons in how they deposit their energy. So these kind of events where the positron annihilates and the two photons are escaping the detector, these kind of events are very similar to actually neutrinoless double beta decay. So we try to reconstruct these events and see if we can discriminate these kind of events from background. And actually we can. This is the peak of energy of this process. You see that there is some background which comes from the Compton scatter of these high energy gammas and other high energy gammas. And here you can see the energy of the extremes of the track that you reconstruct, of the endpoints. And you can see that both endpoints have high energy, it's very, very close to each other. And this is a characteristic of our signal. Instead, background events, for instance, events in this area of the spectrum, have one candidate at high energy, but then the other one is at very low energy. So we have demonstrated that we can actually use this tool to discriminate signal from background. And this is the background measurements that we have done in new. It is very important for neutrinoless double beta decay to have a very good background model. Here you can see in color the background model that comes from Monte Carlo, and with the black dots are data. So our Monte Carlo describes pretty well data. And why is that important? Because you want, in the end, you want to go to the region of interest of the energy of your decay and have just the background events that you expect, not more. Otherwise, you cannot see the signal. So this is also a success of the next wide prototype. The following step will be to build the next 100 detector. That is a bigger version. It will host 100 kilograms of enriched xenon at 15 bar. It will have a higher number of sensors on both sides. And we want to push the sensitivity to neutrinoless double beta decay half-life to 10 to the 25 years expected. Because, well, in new, we still cannot do this kind of searches because the mass is too low. And this, the construction and the operation of Next 100 will be a fundamental step towards the 1 ton scale, which is the following generation of experiments where we want to put together at least 1 ton of isotope of detector. In this kind of future detectors, they need to be extremely radio pure because since you have more mass, if you have also a tiny background, you are done. So in the case of Next, we want to eliminate the photomultipliers because it turns out that they are big and they are intrinsically, they have a lot of natural radiation. So instead of photomultipliers, we are exploring the possibility of reading the energy using also silicon PMs or fibers that would conduct the light far from the detector so that the radioactivity is not important anymore. Also, we are exploring the possibility of using gas mixtures, for instance, helium or CO2, which would reduce the electron diffusion. Because when electrons drift in the gas, they don't go straight, but they slightly diffuse in X and Y, in the X and Y direction. And this blurs your tracking. So this is also something that we are exploring. And finally, the holy grail of neutrinoless double beta decay would be to be able to tag the daughter nucleus of the decay. So in case of xenon, barium. In fact, in this decay, a xenon atom converts into a barium atom, emitting 2 electrons. If one was able to detect this single barium atom, then you would have 0 background. The only background that you would have would be the 2 neutrino mode, but in xenon, this is not important because it's very slow. So that would be really a breakthrough and would be very important for the ton scale detectors. So actually, a few years ago, there was this idea by Dave Nygren, which is the single molecule fluorescence imaging. It is a microscopy technique that allows one to identify single atoms. One has to build a molecule that basically traps the barium atom, like this one, for instance. So this molecule needs a linker that would attach it to a substrate. Then a part that captures the barium atom, and the part that fluoresces. The idea is that this molecule fluoresces in a different way with or without the barium under the illumination of a laser. So for instance, a possible implementation of a detector with this technique would be like that. So you have on one side photosensors that both measure the energy and make the tracking, the measurement of the tracking. And on the other hand, you have a layer of these molecules. And behind you have a laser that goes to the place that you have told them, here there is a possible neutrinoless double decay, illuminates the molecule, and the molecule fluoresces, and you can detect this fluorescence light, and you can tag the barium. So this is work in progress. There are several publications already. It's a long way to go, but it is very interesting. So we have seen that we are using xenon for 2 reasons. One, because it's one of the isotopes that can have neutrinoless double decay, and the other important characteristic of xenon is it's a very effective particle detectors. It can see very well electrons inside the chamber in the case of NEXT. And actually, particle detectors have a variety of applications beyond what is simply the basics physics, so understanding nature and what we are made of. In particular, particle detectors are used in hospitals every day. Well, you can think about X-rays, for instance, but also a particular example is positron emission tomography, which actually uses positrons, a particle of antimatter, to do an image of the interior of the body. So the basic principle of operation of a positron emission tomography scanner is very simple. You have a patient, you inject into the patient a molecule of glucose, which is modified with a radioactive isotope, which emits positrons. So this glucose goes through the body. It concentrates where the metabolism of the body is higher. And this is typically what happens in tumors, not only in tumors, also in the brain in general, where there is a lot of glucose consumption. So after a while, the atom decays, and the positron annihilates with one of the electrons of the surrounding, and emits 2 high energy photons of a very specific energy, 500 keV, in opposite direction, almost opposite direction. So if you surround your patient with detectors, particle detectors, you can identify the line of response, meaning the direction that connects these 2 gammas. So you can cross many of these lines and reconstruct in this way the image of the area where the radio tracer concentrates. And so, for instance, you can reconstruct the position of a tumor, but also you can do a monitoring of the brain activity. For instance, this is the difference between, this is a PET scan, the difference between a brain with a healthy brain and one with Alzheimer, Also, it is possible to monitor the blood flow because the radio tracer is carried around by the blood. So if you have a PET that is long enough, you can see at the same time different parts of the body. And the most common and the most known application is the detection of tumors. So these PET scanners have been in hospitals for a few decades already. And the current technology is to use crystals, so solid state detectors that are coupled with one or more photosensors. Crystals are scintillators like xenon before. So when a high energy gamma enters the crystal, it produces light of some wavelength, and this light is read by these photosensors. The materials that are usually currently in this kind of detectors are high density material like LSO, LYSO, and this is a typical implementation. What makes a PET sensitive? So what are the main characteristics of a PET scanner? Well, what you want is to maximize the number of coincidences that you detect with your device per unit time and per unit of activity of the source. So it is basically this formula. You want to have a good coverage. This factor accounts for the detector geometry. So you want to have a PET that is as long as possible. At the same time, of course, the price increases. So you have to make compromise there. You also want to have a very good detector efficiency. This factor depends on several things, depends on the scintillation time, on the sensor response, on the how many interactions are actually relevant to build this line of response and to build the image. Then, of course, you want a material that stops as many photons as possible. So the ideal materials are the ones that are more dense, but you can also compensate my material that is less dense with a higher thickness of the material. And finally, on top of all these characteristics, if you are able to measure the arrival time of the photons, also you gain a lot in performance in your detector. And this is what is called the time of flight. In fact, if you measure the time that the photons are produced here, and you do the difference, this difference is proportional to the displacement of the emission, the true emission point of the gammas that you don't know, from the center of this line of response. So if you have a good precision, so low fluctuation in these measurements, this translates into a good measurements of this distance. But it's not only that, it's also that having time of flight reduces a lot the noise in the reconstruction of your image. Let me show you with a very simple scheme. This is a normal PET, so you have your two photons. So you have the same probability that is represented by this histogram of the emission point of the photons to be all over this line, right? And the star is the true emission point, but you don't know it. So you have the same probability. You have to cross many of these lines in order to start to delineate the region that is actually the origin of the photons. What happens if you don't have a full line, but you can constrain, you have a segment with the most probability on the center? Well, you can reconstruct your image quite better and specifically with the less noise. So the contrast of the image increases. And this is very important because that means that you can lower the dose of radioactive tracer that you give to the patient. You can reduce the reconstruction time. It's important because, especially for patients that cannot stay still for very long, like kids in pediatric cases, this is very important. So in general, PET scanners want to have a good time of flight, as good as possible. So the idea here is to use, instead of using conventional crystals as scintillators for this kind of PETs, is to use xenon, but not gaseous xenon as in next, because we need a very dense material here. So to stop the gamma. So the idea is to use liquid xenon. Why liquid xenon? Well, we have seen that liquid xenon has two kinds of responses to ionizing radiation, which is scintillation and ionization. And it is transparent to its own scintillation light. So it's very easy to detect the scintillation light. When this happens, the scintillating photon in the BBOv range are emitted from one of the two lowest electronic excited states, the singlet and the triplet. And these states go to the ground state, emitting the photons with two different times. In particular, let's focus on the singlet. This time is very short, it's 2.2 nanoseconds. And this is another characteristic. This is the key characteristic of xenon that could produce a time of flight measurement that is much better than current scintillating crystals. Because if the constant time of scintillation is lower, the fluctuations also are. So in principle, one can obtain a very good time of flight measurements. Also, xenon has a high scintillation yield, so it allows one to do a good energy measurement as well. It is a continuous medium, which is different from crystals, because crystals you have to imagine that they are small units. So each one is grown in a different way, and they can have impurities. And once they are grown, that's it. You cannot purify them. And also you have border effects from one crystal to the other one. Instead, xenon is liquid. It means that it can be purified continuously, and it can be made homogeneous all over the place. This will help with the reconstruction of the signal, because the signal is more uniform everywhere. So these are the basic characteristics of or advantages that can have liquid xenon compared to normal crystals. The idea of using liquid xenon in medical imaging is not new. It has been around for some time. The first one who thought about it was Lavoie in 1976, and different techniques have been tried so far. Some of them were using time projection chamber, as in NEXT. Some of them were using, and this kind of techniques were using ionization also, scintillation and ionization charge as signals. Another group in Japan used only scintillation, but was using photomultipliers. And the only group that is still active so far, to my knowledge, is the group of Zimis in Nantes that use a time projection chamber. And instead of doing time of flight, what they use is a Compton scatter of a third gamma, which gives through the Compton cone, it gives you the same segment that one can identify with the time of flight. It is identifiable with this technique. So here comes Petalo in this scenario. The idea of Petalo is to overcome some of the drawbacks of the previously attempts to use liquid xenon in PET. On one hand, TPCs, the time projection chambers, are complicated because they have the drift time that reduces the rate at which you can take your measurements, the rate of coincidence detection. And also they require high voltages. So it is the operation is more complicated. And on the other hand, also the use of photomultipliers is also problematic. Well, this was decades ago when no other sensor were available. But photomultipliers are not ideal for this PET application because also they need high voltages to operate, so more complexity. And most of all, they are not compatible with magnetic fields. Why is that important? Because nowadays, it would be a great advantage of a PET to be possible to put it inside the magnetic resonance. So you can just ask the patient to stay there for a while, and at the same time you do a magnetic resonance and a PET. So you have two different images of the body, an anatomic image and a metabolic image, with the patient at the very same position. So the idea is to use sensors that are compatible. And so the idea of Petalo is to use the sensors that are the silicon photomultipliers, which are the same sensors that we use in NEXT for tracking, and to use only scintillation light as a signal. So no collection of ionization electrons at all. So why silicon photomultipliers? Well, they come in a variety of sizes, so they are very customizable. They can be very, very small, which is interesting because you want to reconstruct the position of the interaction of your gamma. So if they are small, you have more granularity. They also have a fast response, so you can take data with a fast pace. What is very interesting for the liquid xenon application is that they have a very low thermal noise when you cool them at cryogenic temperatures. Let me highlight that xenon cannot be put liquid at room temperature. You have to cool down xenon to minus 110 degrees, more or less. So you have to put a small fridge in there, but that has an advantage that reduces the noise of your sensors to at a great extent. It actually makes it almost zero. So these sensors are expected to work very well in liquid xenon. Also, they have a large gain, so you don't need expensive amplification. And finally, they are compatible with magnetic fields. So these are the institutions that are collaborating right now in Petalo. It's a bunch of Spanish institutions so far. The possibility of starting the project came from an NERC starting grant 2 years ago. And okay, let me show you a bit the principle of detection of Petalo. This is a scheme of the detector. It's just a hollow cylinder. It's you have to imagine this gray area full of xenon. On the external wall, we cover all the external wall with silicon photomultipliers with an area of 6 by 6 millimeters square. They detect the scintillation light. And the other walls are fully absorbent. So you don't have reflections all over the place, and you can reconstruct the position just very easily just by looking at the pattern on the silicon that are in front of the interaction. This is the energy resolution that we expect to find, because you want to select events with the 511 keV energy deposition. This is the energy that we expect to measure in the detector for one interaction. Liquid xenon has different contributions to give different contributions to the energy resolution. One intrinsic fluctuation that you cannot get rid of is comes from the non-proportionality of the scintillation light and the recombination. So there is a term that you cannot avoid, and then there is a term that depends on your geometry and the photon statistics, basically. So according to simulations, we expect to find an energy resolution of around 13–15% full withal maximum, which is at the same level of the current detectors, of the current PET scanners. Then we want to estimate what is the time resolution that we can reach to do time of flight. So for this, we have simulated the photons and the detection of the photons, simulating also the response of the silicon photomultipliers. And this is the difference, the time difference between the two photons, that we can reach a full lethal maximum of around 300 picoseconds to do time of flight. And finally, how do we reconstruct the position of the interaction of the gammas? So this is our detector. It has a cylindric symmetry. So what we do is to reconstruct the z coordinate and the phi coordinate using a weighted average of the positions of the silicon PMs that have seen light. Okay, so this is an example. This is the cylinder opened on to be on a plane, and these are the two opposite gammas that have interacted. So from the barycenter of these distributions, you can find the position. And the radial position, remember this position into the depth of the ring. This is reconstructed from the spread of light on the silicon PMs. So the closer you are to the event is to the silicon PMs, the smaller is the opening of the light. Once you have reconstructed the position of your gamma interactions, what you want to do is to use them to actually reconstruct the image. So to do so, we have simulated a distribution of gammas in a different way in the middle of our PET scanner. So we have areas with higher intensity. You can see here on the left, this is the true distribution of energy. We have spheres with higher intensity, spheres with zero intensity, and the background. So the idea is to test our detector and see how well this image is reconstructed. To do so, we generate millions of coincidences. We simulate all the interaction of the particles with the detector, the generation of light, the response of the silicon PMs, and the algorithm of reconstruction. This gives you the lines of response. Once you have the lines of response, you use maximum likelihood expectation maximization algorithms that iteratively are applied to recover the distribution, the original distribution. So this is the result, what your algorithm gives you, the reconstructed distribution of gammas. So once you have this image, what you want to do is to quantify how precise, how defined it is. And there are several figures of merit that one can use. One is the contrast recovery coefficient, which is defined this way. You basically compare the amount of signal and the amount of background, the areas that you know that are background. And basically, if it is 1, it means that you have a perfect reconstruction. If it's more, and usually it is more than 1, but in this way you can compare how the contrast varies with different configurations. For instance, varying the thickness of liquid xenon, the reflectivity of the walls, the exposure times, your technique of reconstruction, and this is what is driving us in the design of the detector. So we are actually building a first prototype to test all these things. The first prototype will be a box. So not a real scanner, not a ring. It will be an aluminum box as drawn here, filled with 2.5 kilograms of xenon, and with 2 silicon PM planes on the opposite side of the box. In the middle, we will put a calibration source, which decays beta plus, so that 2 gammas are emitted back to back, and we can see how well we reconstruct them. The aim of this prototype is to measure the energy resolution, the position resolution, and the time resolution of liquid xenon. So to demonstrate the feasibility of the technique. This prototype is being built right now at IFIC in Valencia, in Spain. So here I wanted to show you some pictures of the prototype. Since we have to keep the xenon at cold temperature, we need the vacuum vessel to minimize the transmission of heat. And the vacuum vessel has been built large enough as to host a full ring that will be the second part of the project, the second prototype. We have designed most of these components. We have also, we need a gas system to purify xenon. In fact, in order to keep the xenon always with lower level of impurities and that could affect scintillation light, we circulate it in the gas phase through this system. We have a filter, the hot getter that takes away the impurities. We need a recovery tank for safety reason in case of overpressure of xenon. If there is some heating of the xenon, it will be released to this tank. So no explosions needed. We have a bottle to do normal cryo recovery when you need to recover liquid xenon from your box, from your detector. You use this. Here, here are a couple of pictures of us that are, we have been at home for the lockdown. So we are now in Spain, slowly going back to this so-called new normality. And we are finishing now to mount the first prototype with the gas system. And we hope to be able to mount it all by the end of the month, and in September to start to do the first measurements. So, well, that's it. I hope that I have conveyed the idea that there is a useful symbiosis between basic and applied science, and this has been a very nice example in my experience, because the ideas of Petalo originated actually in looking for the mystery, trying to solve the mystery of the matter in NEXT. And that's it.
So thank you very much, Paola. It's been very interesting, very clear. So let me remind all of the viewers that you can ask questions through the chat. There is like a 15-second delay between our what's going on right now and the transmission in YouTube. So let's begin with the questions from our current audience. So I don't know if there's any I have a couple, but I'd like to see if there's anybody else who would like to ask a question.
I have a question for Paola. Paola, first of all, very interesting, especially Petalo, all the effort that is done for doing all the prototype and everything. So, but my question was wondering, because usually some of the neutrino double beta decay experiment, they, in some sense, they use the same technology that, for instance, the dark matter detector, direct detector experiment. So is this type of technology that is very good to trace the origin of the source can be used for similar aspects, kind of?
For dark matter experiment. Well, the difference between the main difference.
Kind of.
So the main difference between dark matter experiment and neutrino double beta decay experiment is the energy. So dark matter experiments, they want to measure very low energies because they want to measure the recoil, and so a few keV or lower than that, while we are measuring MeV. So several MeV. In the case of NEXT is 2.5 MeV. So at these very low energies, you cannot see a track actually, because the lower the energy the electron, the faster it stops. So this technique is useful for neutrino double beta decay because we have actually a very high energy. So you can see the tracks. There is also another experiment, NEMO, that also sees the tracks of the electrons with the thin foils of several materials. So we are the only two experiments that can do that.
Okay, so for the case of the dark matter, it's just the energy threshold is too low for this experiment. Mm-hmm. But then, since then you're measuring MeV, maybe the same technology you can use it. I mean, not you can use it, can be used in for instance, there are these experiments that they are located outside the Atlas or LHC, I mean, outside CNMS or Atlas in order to measure these long life particles. And then they have to put the detector outside because to have this kind of long time of flight and see the decay can be used in this case because those are going to be much higher energy than
I mean, this technique is I mean, it's calorimetry, so for whatever charged particle it can be used.
It can work. Oh, okay. Cool. Thanks.
Great. Let's see. We have on the chat, we have Paulo Rios, who is congratulating you. He says it's a very nice talk. So I'd like to know if is there any? I mean, do you need to measure for in next the neutrino full beta decay? Because I don't think that you mentioned this.
I didn't mention it because we are still, the analysis is still ongoing, but we are doing that. Actually, we have been running new almost for 2 years. The point is, what limits a bit new is that the low statistics, because we don't have a lot of mass. So we are accumulating slowly as much statistics as we can, and the analysis is still ongoing. So yes, the answer is that we are measuring that. This will not be the first time that the two neutrino mode is measured in xenon, because EXO has also done it. So what we want to do is to measure ourselves and see that it's compatible with EXO, and certificate our ability to identify the two neutrinos at all energies, also at high energy. Yeah.
Right. So on that point, you tell them apart because of the invariant mass of the electrons, I guess.
Yeah, I mean that is the endpoint. So yeah, so we will look only at a very tiny region at the endpoint and see. At this point, you just have to count events, because there is not any feed or whatever you can do. I mean, it's just
right. Yeah, of course, there's just one energy. Yeah, and what about the time scale? So when are you expecting to upgrade to next 100 and the future?
Okay, so we are the schedule was to build this year in Canfranc, but the pandemic has changed all the plans. So we are accumulating delays, but still we will start as soon as possible to make the construction in Canfranc. The schedule now has been shifted to next year, so we hope during 2021 to complete the construction of next 100, and then to start operating. And with the start of the operation, we will also start to think of upgrades to go towards the ton scale direction. But at the same time, we will probably test some of the upgrades in Next 100 itself, or in other, maybe in this detector that is currently operating in Canfranc, we can use it also to test new solutions.
And for how long will Next 100 run?
So in principle, it's scheduled to run 5 years. So, but so we will see. We will see also what we measure, and the possibility to improve the sensitivity or not compared to the current experiments. And also it depends on the improvements on the baryon tagging, because this is a very important point that, if it works, can really change the game. So if this technique works in the next years, it will be probably implemented as soon as possible also in the detector.
And that would allow you to go to lifetimes as large as
10 to the 28, but we are talking about the ton scale. So with 100 kilograms, you are still limited. You cannot do much more than 10 to the 25, 10 times 10 to the 25 or so.
Great. Awesome. Very nice. Very nice. I don't know if there's any other questions from the audience. We have Carlos Pobes saying, congratulations, great job, Paola. I hope we can meet in Canfranc sometime. Best regards.
Yeah. Hi.
Great. And then we have Gerontas Psi.
This is Hi, Panos.
I know him also, right? I think.
Yes.
I think, yeah. So she says, hola, Paola, nice talk, nice name, Pétalo. Do you know the efficiencies of barium tagging, barium capture, detection overall?
No, this is something that needs to be studied. I mean, just there are so far there have been a few publications with demonstration in very specific environments, which are different from the environment of NEXT, which is high pressure. So, in principle, the efficiency, I mean, would be, let's say, this kind of technique wouldn't give you any false positive. I mean, it can only detect barium, that's for sure. Maybe it doesn't have 100% efficiency. So maybe you don't get all of the barium that are there. That is still to be quantified, but it shouldn't give you any false positive. No background should pass this filter, let's say.
Great. So let's see if there's any follow-up, since there's a 15-second delay. So any questions from the audience? Again,
yeah, I have a very small question. Just,
go ahead.
I mean, not a small question, because since you know that I'm not from the experimental point of view, so for me it could be more naive, but very complicated for realize. But in the sense, when you were describing your detector, Petalo, you were assuming to use a cylinder to put the photodetector and all the tracking of the. Is there any other geometry that can be used for that could
well,
be?
a cylinder is, let's say, the simple thing, because you can put your patient on a bed, and then you have to surround the patient in some way. So the cylinder is the most practical way, I would say. Also, geometrically, I think that it's easier to reconstruct the position if you have everything at the same distance from the axis. So I don't know of any PET with other shapes, but I may be,
Yeah, I guess it's the same. No, because I was thinking maybe instead of a cylinder, something more bulk in the center and more.
What would worry me of that is how do you reconstruct the position? I think that it would be more difficult to really understand where the gamma is, but I don't know. I've never seen any of that.
So, and another question related with that, because I heard many, I mean, since there is all this stuff with machine learning thing that is kind of gold in this sense, they are using this technique also to improve the reconstruction for the PET. So
yeah.
is plan to use it also in your case?
Yeah, actually this is one of the lines that we are pursuing now. We want to use DNNs to distinguish photoelectric interactions from Compton interactions. So I haven't mentioned in the talk, but one of the problems of PET reconstruction is that if you have a Compton interaction, meaning two interactions one after the other, that spoils your reconstruction because you have a pattern that is not always easy to reconstruct. So this is something that we are looking into, if it's possible to use deep neural network to distinguish this kind of events, because so you can single out the photoelectric, and then with the Compton ones, you don't need to throw them away. You can think about a smarter way of reconstructing it. But yeah, so this is an example of application, yeah, of neural network in data.
Thanks.
Great, super. Then, okay, we have Eduardo Peinado saying very nice and interesting talk.
Hi, Eduardo.
Yeah.
It's nice to have so many friends here.
Yes. There's a lot of people who, right? Okay, so I think that's it. We don't have any more questions on the chat. With this, we are closing the season with webinar number 99, and we are taking about two months of a break before we come back with a surprise for all of you in webinar number 100, right? So we will be celebrating with pisco and aguardiente and something else. I don't know. Right. So anyway, take care. Hope you do well on these two months, and see you soon. Thank you, Paola, once again for this fantastic webinar.
Thank you all.
So